Hello, we are Team Hydronics. Our project focused on designing and testing an air lubrication system to reduce the resistance experienced by small-scale model ships. Large ships already use this concept. They eject air under their hulls to reduce contact with water and improve efficiency. Our goal was to see if we could recreate this effect at a much smaller scale with a 50 centimeter 3D printed boat. The key question we asked, can injecting air under a small ship actually make it more efficient? After studying designs used by advanced marine tech companies, we found many of them use air cavity hulls. So we implemented cavity slots on the bottom of our hull. These help trap the air bubbles and reduce direct water contact. We went with flat bottom hull, which increases the contact area of the air layers and gives more stability. The entire ship was designed in CAD with air delivery features built into the model. We then 3D printed the ship in sections for better print quality and easier assembly. During assembly, we had to trim and rework some parts to properly fit all the electronics, wiring, pump, and battery within the hull.
For the air delivery system, we tested PVC, silicone, and polyurethane tubing. PVC was too rigid and silicone collapsed under pressure. PU tubing was perfect, flexible, airtight, and had a slippery inner wall that allowed fast airflow. We used pneumatic push-fit connectors which prevented backflow and kept the system leak-proof without restricting flow. We used a 250 liter per minute pump with 4500 pascals of pressure to feed a 2 diffuser setup. One diffuser was placed at the front of the hull and the second about 3/4 down the ship's length. These were made using copper pipes drilled with 0.6 mm precision holes, allowing us to release thousands of small air bubbles directly beneath the hull. The bubbles then fill the cavity slots, creating an air layer between the hull and water. This is the key working principle of our air lubrication system. We tested the ship in a controlled pool using a stopwatch and an accelerometer. With the bubbles off, the boat moved at an acceleration of 0.64 meters per second squared. With the bubbles on, it moved at 0.54 meters per second squared. That's a significant drop in energy use, showing a 6% gain in overall efficiency when the air system was active. Our tests confirmed that lubrication works even on small-scale RC boats.
During our early trials, we faced some major challenges. First, the boat would curve to one side while moving forward. We later realized this was caused by the flap being installed unevenly, which created unbalanced drag. Once repositioned, the ship moved straight. Another issue was water leakage into the hull. Since the 3D printed parts are not fully waterproof, water started to seep into the infill structure, adding weight and eventually causing the ship to sink. To solve this, we applied strong waterproof sealants along all joints and layered parts. We also ensured all electronics including the battery, ESC and pump wiring were firmly secured and protected inside the hull to prevent short circuits or water exposure. These fixes made the ship stable, watertight and reliable over multiple test runs.
In the end, we built a working ship with a cavity-based air lubrication hull, dual diffusers placed at optimized positions, powerful but lightweight pump system, and a 3D printed structure custom built for performance and experimentation. We proved that air lubrication can improve efficiency and learned how to apply real-world marine engineering principles into a small, testable model. From CAD modeling system to design, testing, and troubleshooting, this project taught us more than any textbook could. As the group, we were proud of how we overcome problems and work together to bring this idea to life.
We are Team Hydronics and this was our air lubrication system project. Thank you.